which we have the details of the class, including objective grading policies, will be one midterm, one final. There will be in-class quizzes and homework. The class doesn't require a specific textbook, but there are some reference books that are very good. For example, Elasticity by Barber. Professor Tai used that a lot in his lecture note, and also Fractional Mechanics by Anderson. But for the sake of this class, it's good enough for you to just refer to the lecture note that's being uploaded on Canvas. And then also you can check the course outline based on the syllabus. Okay, and if you have any questions about if you're on the wait list, about your enrollment, or in general, administration related question, please email Professor Tai directly, and his email is also on Canvas. So before jumping into the lecture, we would like to begin with two simple concepts that you guys probably already know. Since we're here for ME 340, mechanics, elasticity, and inelasticity. Regarding the name, what is mechanics, what is elasticity, and what is inelasticity? So mechanics in general is trying to describe the behavior of solid materials using mathematical theory, try to describe deformation, motion, fracture under internal or external forces. For elasticity, and inelasticity, what's the difference between elastic deformation and inelastic deformation? For now, it's good enough to just think about elastic deformation and inelastic deformation as, or specifically plastic deformation as illustrative example. If you look at your skin, you deform it, you apply external loading, and then you deform the material, and then you unload, and then the material goes back to its original shape. That's elastic deformation. And if you take a piece of metal or your eyeglasses and you deform it, and then you unload, and the material generate a permanent deformation, which is a plastic strain, and that's a plastic or inelastic deformation. Okay, so that's just the course name, what this course will be covering about. So what will be covered today? There will be mainly just two things. The first part is we're going to use 3 examples to illustrate what is stress, strain, and then we'll be going over a preview of a set of questions, problems that is going to be covered in this class, in the whole ME3 course. And the second part will be coordinate transformation. Specifically practicing the concept of index notation and tensors. So you'll be hearing the term tensors a lot in this lecture and throughout this whole class. And that's a very important concept that we're going to use in the class for a graduate level of solid mechanics class. So as we already mentioned, what's elastic and inelastic deformation. For today's lecture, we'll be mostly using elasticity theory. And specifically for this class, for ME 340, we'll be mostly assuming specifically linear elastic under infinitesimal strain or infinitesimal elasticity. And more specifically, a small deformation. We'll be describing solid behavior when the deformation is small. And later in this class, you will understand part of the reason of assuming linear elasticity, infinitesimal strain is, especially linear elasticity, is it's easier to apply superposition. But we will not cover that today. And also the second, sorry, that's the first thing. And also, for this class, we'll be mostly covering problems, solid mechanics problems, that is static equilibrium, So we'll not be focusing on dynamic problems or non-equilibrium problems for this class. And in this whole lecture for 340, you will see a lot of variables and equations. So here is a preview of for today and for the whole class, what kind of variables we'll see. Variables, and also in general, what equations will you guys be learning and using in the lecture. So for the variables, you will be learning specifically today about the concept of stress, strain, and we can actually use different symbols to represent sigma, epsilon. And I draw two lines underline as to represent as a second order tensor, which will be introduced later. For now, you don't have to worry too much about a symbol. And of course, you can use other letters or symbols to represent displacement U to the vector, traction force, so vector, and elastic constant, which is a constant. Can tell by this name. And for the equations, we'll be learning, as we mentioned, we're mostly doing problems involving static equilibrium. So you guys will be learning equilibrium equation, equation of compatibility, which will not be covered today, but it's good that you know this, and when we encounter this in the future lectures, you understand, and also generalize Hooke's law, which I assume all of you guys probably already learned what is a Hooke's law in your high school classes. And so what is generalized Hooke's law in the context of solid mechanics that we'll be using a lot of tensor calculation, tensor algebra. Okay, and now I will officially begin with the examples as we promised for the 2 point.
Okay, this comments.
Yeah.
That's probably like quasi-static equilibrium.
Okay.
The next to the content.
So under what part is it quasi?
Because there is a movement, there is a displacement. If it's static,
Yeah,
it's like
that makes sense. Yeah.
And you're gonna cover all of these in this?
But under infinitesimal elasticity, we don't distinguish reference and current configuration. So yeah, I mean that also correct. Yeah, there's just like very infinitesimal small motion, which I mean you can call
we
it
define the displacement, right? We define displacement as the original, so small x and big X.
Yeah.
So
and in this class we don't distinguish small and big X.
We do. That's how we define displacement.
Yeah, only when we define displacement, and when we later on move to displacement, we assume the current and reference configuration are the same.
Right. Yeah.
So
are you gonna cover all of these in this one lecture?
For this lecture, we will not be covering compatibility, but this part in general is in the lecture note number 1. So I guess it's kind of necessary to go through it. So I'll officially begin with an example.
Okay, so you mean this is the content of the entire class?
Yes.
Not this lecture.
Yeah, up to here. And for this lecture, this is the lecture. Oh, sorry. For this lecture, this is the content.
Let's see.
This lecture. I kind of blended in. So what kinds of problems? Maybe I need to write it out, but are we going to solve using elasticity theory? Example number 1, we begin with a very simple example. There is a elastic bar, and that's a rectangular or square cross section. More precisely, if A and B are different, it's rectangular. So the elastic bar has a cross section, has this width A and height B. and you apply force F as length L. And when you apply a force F, the bar will deform a little bit. So it's called the deformed change of length is delta L. And we can establish a coordinate system, a Cartesian coordinate system, called X, Y, and Z, which I assume you guys are probably very familiar with this. So then we're going to introduce, as I promised, stress and strain. So when you apply a tensor loading to this elastic bar with a rectangular cross section, we can define the axial stress. And if we already established this Cartesian coordinate system, the axial stress in the z direction, we can first just write it as sigma zz, and later I will explain why it's sigma zz. It's calculated as force over area. So what is the unit of stress then? Anyone can tell me? It's probably some student gonna say it's a force per area, which is Newton per meter, which is Pascal. Sorry. And we can also define this is the axial stress. Okay. And we know there's a change of length in the z direction, which is the axial direction, axial loading. So we can then define axial strain, which is also epsilon zz, as we use the symbol. And axial strain here is a change of length delta L over L. Fine, that's that. And what's the unit of axial length? So you can easily see that is if you use SI unit is meter over meter, which is unitless. So this is axial strain. And as I mentioned in this class, we'll be mostly using linear elasticity theory. So using linear elasticity theory, according to Hooke's law, what do we know about the relationship between stress and strain? According to linear elasticity, based on Hooke's law, the relationship is written as sigma zz equals the elastic constant times a strain in a z direction, in the axial direction.
I have a question.
Yes.
So for this object, you apply the force on the top.
Oh,
Isn't that gonna move? Okay.
And we have three equations and we define the variables. So if you substitute the equations, you naturally end up with a very familiar result that you guys already seen in your previous course, undergraduate course, mechanics materials, which is that you can obtain a change of length, the elastic bar equals, you just plug in an equation, we'll see it's force times, capitalize L, sorry, force times length divided by Young's modulus times area. And if you want to be more precise, the area for the rectangular cross-section bar is A times B. Okay, so we call it case A. And on top of A, can we introduce a more interesting problem or example? So we can keep the same rectangular cross-sectional elastic bar, apply the same tensile loading, also have the length L, A and B. And for now, only difference, which we kind of go into the graduate level of the level part of this class, is we introduce a geometric difference in the material, where you have a cylindrical hole. And so the only difference between A and B is the geometric difference. You apply the same loading, right? But given this cylindrical hole, you can probably calculate the new cross-section area, which call it A prime. And it's quite easy to see that if you first define a radius, the geometric hole is R, then a new area, A prime, under this geometry is A minus UR times B. And what's the key difference between example A and example B? Example A, you apply the force, and then there's a cross-sectional area, but there's no geometric difference in the elastic bar, so the stress is uniform. For example B, because there is an internal cylindrical hole, so we know the stress distribution will be different around the hole. And that is where we know that there are variation of stress and strain around the hole. We call it a stress field. So let's say first, and got the stress distribution for now is not uniform. And you can first calculate the average normal stress. So if we define average normal stress, you can call it sigma sigma bar or sigma average, whatever name you want to call this. So for now, if I call it sigma bar ZZ, it can be written as we have a new area, apply the same force, and it's F divided by A prime. And since we know there's a stress distribution difference, there's a stress field around the hole, we can know that the stress distribution around this spherical hole, or cylindrical hole, the stress will be much higher around the hole, sigma ZZ, and it gradually decays as it's further away from the geometric hole we introduced. And the same here. If the cylindrical hole is in the center of the material. So how do we characterize or mathematically describe this stress variance or difference? One way to define or describe this is we introduce a concept called stress concentration factor. How do we use this? Which we can first calculate the maximum stress, or if we know the maximum stress over the whole distribution around this hole, we call sigma ZD max times, it got to be some constant, some variable times the average stress, which we just defined right here. So what is this factor? We then call it a stress concentration factor. You can call it K. You can use whatever letter you prefer. So if you plug it in, it's written in the form of K times force divided by the new area, A prime. And in this class, you will learn how to derive the stress concentration factor for different geometries, for different problems, which is very interesting and also practical for your daily research. I know a lot of you guys are from geophysics department, a lot of you guys from civil engineering, from mechanical engineering. So in geophysics, for in environmental research, there'll be a lot of problems that you have material defect or internal variances, and you have stress distribution, and then learning how to derive the stress concentration factor will be very important for your research. In this case, if the length A is much larger than the whole radius R, under this case, I'm just gonna give you guys an answer for this problem. The stress concentration factor is 3. Now, what if we make this problem slightly more interesting? As I promised, there will be 3 examples. So now we have a geometric difference based on this hole. What if the cylindrical hole is not a perfect sphere, a perfect circle right now? What if we turn into an elliptical shaped hole? Then it will look something like this. this. And same, you apply force and cross-sectional area. Today, I will not derive this or give you the answer for the elliptical hole, but you can kind of imagine, given a spherical hole, if we call for elliptic, call this alpha and call this beta. If beta is getting shorter and if we fix alpha, then the aspect ratio of alpha divided by beta is getting larger. Intuitively, what would you expect the stress distribution to be? Is it going to be larger or smaller? And some students are going to say larger, some smaller. So I'll say the students who answered larger, your intuition is correct. The stress distribution will be larger when the spherical hole is turning into an elliptic hole. Compared to this, and you will learn how to derive the stress concentration factor. Now, what if we extend this example and turn this hole into extremely flat? If you shorten beta, we call it flatten the hole. If you turn this hole extremely flat, where when beta goes to 0, then it becomes a defect or crack, which this is also an important problem in different engineering fields among you guys' research background. As you're gonna learn that when you have a crack, a defect, that the height of this hole is infinitely small, what will be the stress concentration factor or the stress distribution around this hole? If you're any guess, any potential answers for this problem? And if some students say, oh, if that becomes infinitely small, the stress will go to infinity, then you're correct. And if some student ask the question, and what is the physical interpretation of stress goes to infinity, is we do not have a representation of stress going to infinity because stress should not go to infinity. And then you will need fraction mechanics to describe how will crack propagate, and that will be being taught much later in class. And that will solve the problem, help you understand why does stress goes to infinity. So this is the case of crack. And at the crack tip, how does the stress? What is the stress distribution? I'm just going to provide you guys the answer, and you will learn how to derive it much later in class, which the stress distribution correlate with, it's called radius r. It's a very important relationship. It correlates with 1 over r square root of r. And as r goes to 0, and you can see the stress goes to infinity. Okay. So far, we finished A, B, and C, the 3 examples to illustrate stress and strain, and also a general set of preview of the question or problems you're going to learn in this lecture, which you will learn how to derive complex stress concentration factor and the problems related to the thing that we have shown here. And finishing the first item, I'm going to now go to the coordinate transformation item. Before I go to the second part, just going to comment on this. As we have introduced, we define axial stress and strain. And we use the notation sigma zz, which later you will understand why, because it represents the stress on the z surface or z cross section or z surface pointing to the z direction, and there will be many stress components according to using this index notation. Okay, now I'm going to do the second part. And in the actual lecture, I will take a picture for this before I wipe it. But for now, for sake of practicing, we won't wipe it. Okay, so for coordinate transformation, we're gonna start with the continuum potato, which if any of you guys already take continuum mechanics or any solid mechanics, graduate level mechanics class, you're probably very familiar with this concept. You can assume there exists an elastic body, the shape of a potato, and you can apply some and call it B, and you can apply some boundary condition. For example, you fix some part of the bottom, and you can also apply some loading, mechanical loading. And we assume, as we previously mentioned in the beginning, we are assuming static equilibrium, and you can establish a coordinate system within the body, X, Y, and Z. And after you apply any loading to this elastic body, you will generate deformation and you will generate a displacement. And for this displacement, it can be characterized as a displacement vector. So using this established coordinate system, you have three basis vector. We now call it X, for X, Y, and Z axis, the basis vector E1, E2, and E3. And to represent the displacement vector, we can write in the form of U, the underline, or it can be a tilde line. Vector U equals, there are three, you use the three orthogonal axes to represent U as U1, E1, which E1 is pointing to the basis vector for the X direction, plus U2, E2, plus U3, E3. And since it's represented by three basis vectors, we want to simplify this expanding of this long formula. And one way to simplify is, since it's U1, E1, U2, E2, U3, just saying, right, U something, E something, we can write it as UI, EI. So what's that called? That's called Einstein notation.
So what's the difference between E1, E2, E3, and X, Y, Z?
X, Y, Z, you can just use it to represent the three axes, name it X, Y, and Z. And for X, the basis vector for X is E1, which under this coordinate system you can write as 1, 0, 0, and for Y is 0, 1, 0, and Z. And when you sum it over for the actual displacement vector, it's also a vector. It can be some value 0.2, 0.3, or whatever.
So they're basically unit vectors.
Yes. Yeah, I should mention it. Okay, this is unit vectors. I'm gonna mark it.
So you probably want to define them as maybe the
Yeah,
X.
it's better. So I should define these are three unit vectors.
So X over X.
Yeah,
Okay.
yeah.
Like X over X. Yeah, something like that.
Do you think it might take a bit more time? Anyway, I think it's good to define it to be more precise. 0, 1, 0. And this is let's see. Same Y. It's a vector. Okay, cool. And for UI, EI, this displacement vector can also be written in the form that if you take linear algebra form, you're very familiar with U1, U2, U3. And we're using UI, EI to represent the summation on index I, because we're summing U1, U1, U2, E2, U3, E3. We're summing over all the axes, our indices. So without writing explicitly the summation sign here, this is called Einstein summation. And when you see UI, EI, or something, J or K or UJ, EJ, UK, EK, you see the index is being repeated twice. It's called Einstein summation to represent the summation operation. So the displacement vector exists, and to represent this displacement vector under this coordinate system x, y, z, we can write it in the form of u1, u2, u2, u3, u3. And what if we slightly change the coordinate system a little bit? For example, this origin, we slightly rotate the coordinate system. And we have 3 new unit vectors to represent the rotated coordinate system, called E1 prime, as previously defined, and E2 prime, and E3 prime. So under this new coordinate system, the displacement vector can be represented in this coordinate system as U1 prime, U2 prime, U3 prime. And again, I have to mention, I forgot to mention. So the index I is repeated twice. So that's called the index that's repeated twice. In Einstein notation, that's called a dummy index. Okay, cool.
They're always looping through 1 to 3.
Sorry, what?
The dummy index, is it always looping through 1 to 3?
In 3D, yes. In 2D, it's 1, 2.
I'm asking this question because, like, later on, we might introduce the void notation where we have like actually like 6 values.
Yeah, so that will be lecture 2, right? That will be your part.
Yeah. So
Okay.
basically, for that case, this
Yeah.
this notation is not applicable.
Yeah. Yeah, that's a good point. Well, I doubt student will ask that, but let's
Yeah, I
assume
think
someone.
this is a simplification of like a sum. So you probably should have a sum
Yeah.
at the beginning.
Yeah.
I from 1 to 3 of this.
Yeah.
And it's just like for
Yeah, which I do have
simplification.
later. Yeah.
For simplification, you just remove that sigma sign.
Yeah, sigma I equals 0 to 3.
Yeah.
1 to 3. And I guess in real space, in the real physical space for 3D, represent a vector in the physical space that's 1 to 3, but it is not necessarily always the case. You're not doing the physical space, for example, the way notation you try to simplify 3 by 3 matrix or tensor into a simplified form. Then just to emphasize, this I is not necessarily always represent the physical space axis. So after the coordinate transform from E1, E2, E3 to E1 prime, E2 prime, E3 prime, the origin is fixed. How do we characterize this operation of transformation? We can define a matrix called Q, which is the rotation matrix, and characterize the rotation from one coordinate system to the other coordinate system. Has 2 index I and j, and is the dot product of the new coordinate system, the unit vector of the new coordinate system, times the unit vector of the old coordinate system. So here it might be helpful to pay more attention on the indices. So Qij is EI, which is the new coordinate system, dot EJ. So that's by definition. And this Qij is an orthogonal matrix. So orthogonal, and which means if you take linear algebra, you're probably very familiar with this part. It means the inverse of the matrix equals the transform of the matrix, which is a property of the orthogonal matrix. And we want to use the defined matrix, the rotation matrix, to describe the transformation process from one coordinate system to the other coordinate system. We already know that under different coordinate systems, the displacement vector can be written or represented differently. U1, U3, U1 prime, U2 prime, U2, U3 prime. So to use the rotation matrix to represent the transformation process on the displacement vector, we can write in the form of this, just ui prime, which is this, equals the rotation matrix and product the displacement vector in the original coordinate system, uj. Okay, here you have to pay attention. Previously, one of the students, Dr. Ivan Wang, mentioned that this is actually a simplified form of sigma I, or I equals 1 to 3, or you can generate sigma I, ui, ei, and Einstein summation basically simplify this form. So this is the same. As you can see, what index is repeated twice? Here is index j. So again, as we identified, index j is a dummy index, and index I is a free index. So dummy index is being subbed over. So this is a simplified form of j and qij, uj, and this is helpful information that you later will be using a lot. And this is called free index. J is the dummy index. And we can also generalize this formula to not just the displacement vector. So if you want to generalize, you can call it any vector A equals qij aj, and that's for the general case. So for now, you guys already learned what is index notation, what is Einstein notation, what is a dummy index, what is free index, and a general rule of applying how do we use index notation to represent transformation, coordinate transformation.
Yeah, so that Q matrix is an orthonormal matrix. If it's orthogonal matrix, it is Q equals QT. If it's a Q inverse equals to that, it's orthonormal matrix. Okay. Can
you check the lecture note whether this is?
Yeah, this should be, or
yeah, you can check on Canvas. Maybe I wrote it down wrong. Yeah. I'll mark it in my note.
If it's orthogonal, it's just gonna be U equals QT.
Okay, some practice for the index notation. So I'm gonna give you guys a simple example, and I hope you guys can use what you just learned here to check whether.
Okay, here's also orthogonal matrix.
So that's a tiny mistake in the lecture note.
Orthogonal matrix.
Okay, I mean we can mark it and then check it. So first example is I'm gonna give you guys equation. I want to see whether does this make sense using a rule that we just learned. Equals vi. So does this formula looks that it kind of makes sense? It agrees that we are summing the dummy index correctly.
It's equivalent. Orthogonal matrix is equivalent to orthonormal matrix.
Okay.
Cool.
And let's also agree with when we talk about free index. Anyone can help me and see whether any students are interested in joining this discussion. So given what we have just discussed, we look at it, I is repeated twice. So here I is a dummy index. It's being summed over. So if we expand this, it should be summing over I, and J should be the free index. So if you're using index notation, this formula should end up with a free index J, but here the free index turns out to be I. So this formula does not make sense. According to the rule that we just learned and define and learned here. But yeah, okay, cool. And another example would be this is not minus, this is bullet point. Would be UK, PKJ, UJ. So what would this be? And any student can help me answer this question. So here, as we see, what's the repeated index that is the dummy index? J is repeated twice, so we know that J is being summed over, and so that's dummy index J. And also K is also being repeated twice, so K is also a dummy index. So as we can see, if you do the operator separately, here first, if you do summing over J, then the only free index is K, so you know with a vector with some free index K, and then you sum over K, which K is also dummy index. So this will end up to be a constant. And in the real space, it just is a scalar, right? But in general, this can be any values, but which is a scalar. Okay, in summary, this is something that we have repeatedly emphasized, but I'm going to re-emphasize again because this is very important in this class. That you guys have to pay a lot more attention, which is if you see a formula A, I, J, J, whatever, any related problems that involving index notation, any index that's being repeated twice is called a dummy index, which means that this index is being summed over. So this is a simplified form of summation of AI, J, Uj. And if J is in the physical space, in the 3D space, then it's usually J equals 1 to 3, but it's not necessarily the case in general, but it's being summed over J. Okay, so we define a displacement vector, and using this vector, we kind of introduce what's the coordinate transformation, and now we'll gradually go to tensors. So recall the first example, the first part, we introduced 3 examples. We first have a uniform geometry, and then we kind of introduce some geometric variance, and there will be a stress different distribution. And I mean, we generate a stress field because there are some internal differences. And what if there are some displacement differences among the whole field? So what is a displacement field? Using a coordinate system X, Y, and Z, and you have this continuum potato. Have any mechanical loading. And if we define this as capitalized X, Y, and Z using this coordinate system, and let's represent this coordinate system as X, vector X, which means X, Y, and Z. And after this material slightly deform, the coordinate system also slightly change. And this is called the new coordinate system, little x, y, and z, and can be simplified in the form of little x underscore or little x tilde, if you wish. What is a displacement field? Using a Lagrangian viewpoint, or in the simpler form, you can imagine this is a balloon, and you can use your marker to mark some points on the balloon, or it can be rubber, it can be an eraser, and if it deforms, you can track the motion of different material points. For example, this point moves here, this point moves to here, and this point moves to here. And you use this new coordinate system to represent the new the deformed case. And we can call this coordinate system represented field called configuration. So this can be called the reference configuration. This will be called the current configuration. So what is the exact definition of the displacement field? The field will be the current configuration minus the reference configuration, and that's the exact definition of displacement. Okay, again, I might have already wiped that part, but I have repeatedly emphasized that in this course, in ME 340, we are using the infinitesimal assumption. So under infinitesimal assumption, the displacement field is approximately the same in the reference and current configuration. Which means that in this class, you will not need to distinguish the difference between the reference and current configuration. Which, if you're interested in learn how to represent the large deformation, which you have to distinguish the difference between the two fields, you can take continuum mechanics, which you will learn how to use deformation gradient tensor to represent the transformation of field. And based on that, you can define new stress and strain represented under different configuration. But for the sake of this class, to derive the analytical solution that we'll be deriving are based on assumption of infinitesimal small deformation, which means that there are no differences between the two configurations, and the displacement field are approximately the same under the two coordinates.
There's a comment on this.
Yes.
So there's actually no change of coordinate system in defining the displacement field. So basically that big X is a vector that basically two of them are using the same E1, E2, E3. It's just the value of the big X and small x are different. So there's like no coordinate system transformation. It's using the same coordinate system. It's just like the numbers are changing. For example, if that big X is 1, 1, 1, and that small x is 1, 1, 1.1.
That's a good point. So maybe I should.
Yeah, so it's still using the E1, E2, E3, using the same set. So that's basically in the notes. Equation 12 and 13 are defining them. Yeah, you can see here. You can see that they're defined just the coordinate numbers are different, but the
basis vectors are the same.
The basis vectors are the same. Then you can define that. Then they can actually like minus each other to get the displacement. If they're under a different coordinate system, they cannot do that.
I'll revise the part. Okay, so what is the displacement field? We establish a coordinate system, and the coordinate system is not changing. We are not transforming the coordinate system. But under this material body, we first define this configuration where we represent all the points as vector form of capitalized X, which we call reference configuration, and then we transport the body to the body. Now we could track the different material point. Then you have a new vector that represent all the points in this material, which is little x, and the displacement field is defined exactly as a difference between the current and the reference configuration, which is little x minus capitalized X. But for the sake of this lecture or this whole class, under infinitesimal assumption, there are no difference between the two configurations, which is still under the same coordinate system, the same basis vectors. But the displacement field are approximately the same. Okay, that's a good point. Okay, and if you already taken any course that involve in differential equations, whether ODE or PDE at Stanford or elsewhere related to mathematical analysis, one intuition is you learn what is the exact definition of displacement field. You would naturally want to ask what are the gradients of displacement. Because physically, a lot of theory in physics are derived based on gradients or differential operations. So in general, there are two types of gradients, temporal and spatial. So for temporal gradient, which will not be covered in this class, I'm just introducing the whole set for you. So it flows better. So the temporal gradient is just the time derivative t of the displacement field. Either you can write it as u dot, which is the rate. But in this class, as we are mostly wipe it, but if you recall it, if you still remember, we're mostly dealing with static equilibrium problem. So we'll not be dealing with a rate, and we'll be mostly dealing with the spatial gradient of the displacement field. So for example, you can do partial x of the displacement. You can also do partial y. You can do partial in the 3D space. So if we use index notation, partial ui, partial xj, using the Einstein notation, we can simplify the gradient representation as ui comma j, which I can be x, y, z, or 1, 2, 3, and j also can be 1, 2, 3. And again, y can be the same with j, which means if I can be the same with j. So if I equals 1, j equals 1, then it's partial u1, partial x1. And also be partial u1, partial u2, partial u1, partial x2, partial u1, partial x3, etc. Okay, so this is by definition. This is also Einstein. And another question to audience, to the student, what is the physical meaning of the spatial gradient of displacement? Does anyone think this is the strain? If you think this is a strain, you're quite close, but not there yet. Why is that? Because you can expand partial ui, partial xj as partial ui, partial xj, partial uj, partial xi, plus 1/2 partial ui, partial xj, minus partial uj, partial xi. And why would I want to expand this in this form? If you're familiar with, I guess, if you're familiar with this representation, this is trying to symmetrize a matrix. Well, if you're familiar with linear algebra, I guess. So this part is symmetric or symmetry, right? It satisfies symmetry. And this part actually is anti-symmetric. Symmetric. And by definition, the symmetric part of the spatial gradient of displacement is the strain. And this antisymmetric part characterize or represent rotation. To be precise, we can define different Greek letters that we define strain as epsilon. This epsilon ij by definition is 1/2 ui comma j plus uj comma I, and it's being symmetrized. In antisymmetric gradient, can use omega. This is the infinitesimal strain, and this is the infinitesimal rotation. The small strain, small deformation strain. And the strain, we look at it, we can also has two index, I and j. And now we're gonna go to tensors. So strain is a tensor. And it is, we define, or we call it a rank, so we didn't define, we call it a rank 2 tensor. Or second order tensor. Why is that? Because it can be expanded as two indices. It can be expanded, first written in the form of double underline or a tilde. It can be expanded as epsilon ij, ei, ej, where ei and ej are the basis vectors that represent strain tensor in the form of a matrix epsilon ij, and same for the rotation tensor. And as we already introduced here, when you want to transform the coordinate system to represent the displacement vector, we have two coordinate systems. You need a rotation matrix Qij to represent the transformation process. Here, since epsilon is a second order tensor, it has two indices. So we have to, so we want to transform. There's a bullet point right now. Yeah, so we want to transform the coordinate system. There are two indices. We need to multiply the rotation matrix twice to rotate I and j. So let's say we have a strain tensor under the coordinate system Mn, and then I want to transform. Want to transform the coordinate system to represent the same strain tensor into epsilon ij, and the transformation process can be written down as two rotation matrix apply to the two indices, respectively, M and N. So I want to transform, rotate N to J, and also M to I. Okay. So transform the coordinate system. Again, physically, the strain tensor is the same. And computationally, how would you represent this transformation of the coordinate system? You don't have space. Why? So in code, let's say in the case of MATLAB, I can do epsilon prime, because transforming epsilon mn to epsilon ij prime, transforming index n to ij prime equals 0, so 3 by 3, assuming we're living in a 3D space, and it can be represented in a form of matrix. Since there are transformation from n to j, m to I, there are 4 indices involved. So in MATLAB, we can do a for loop, or, and this is quite important for your homework too. There are three indices, so 1, 2, 3. For j equals 1, 2, 3. For m equals 1, 2, 3. N equals 1, 2, 3. Epsilon prime ij equals epsilon plus q by m times, because since we're applying the rotation matrix twice, q j comma n epsilon. There's no prime here because we're just multiplying the original strain. Strain tensor represented as a form of numbers in the form of matrix. And then in MATLAB, you don't want to print it out, and you can end the loop. Okay. Again, MATLAB is not the only way to represent it. Also, it can also probably be represented in the form of epsilon prime equals. You define the rotation matrix properly before you apply it in epsilon. There's no prime here times epsilon. Okay, but MATLAB is not the only way to represent the transformation, and you can also use Python, NumPy, also Julia, but for the sake of time, I'm just going to briefly go through the Python one. In Python, if you like to use NumPy, which nowadays is very common, you can simply write epsilon prime equals NumPy. If you import NumPy as NP, and it's NP dot isum. So there's this package. There already exists in NumPy package. Same for Torch too, and you also many other packages. Let's say in the case of NumPy, it can also be written as quote im jn mn 2ij. This is very intuitive because this corresponds exactly to the index transformation process. As you can see, this is im, jn, mn, and m is the free dummy index, n is dummy index, and something over ij is the free index, straight to ij. So it's very intuitive using Python. And if you define q properly before this, like in MATLAB, then you can q epsilon. Also can do similar with Julia. And if you're interested, come talk to me after the class. Cool. So we already defined the strain tensor properly, and we know that by definition, strain tensor is symmetric, and also the rotation corresponds to the anti-symmetric part. Because strain. Physically, it corresponds to the stretching body, it takes energy, so that's why it's symmetric. So by definition, strain is a symmetric part of the spatial gradient of displacement. What about stress? We want to properly define the stress tensor. So there exists this elastic body on the coordinate system x, y, z, and we have 6 surfaces, and under each surface there are 3 in 3D. There are 3 stress components. So let's say for this surface is in the y direction or the 2 direction. So this is called a 2 surface or y surface. And this surface, all the stress, the first index are 2 because it's in the y surface. And the second index of the stress tensor corresponds to the direction of the stress tensor component. So for this component, it's pointing toward y direction, so it's y22. For this component, it's pointing towards z direction, so 2,3, because 3 is z. And for this tensor component is 2,1, because pointing toward x direction. So there are 2 ways to teach this. One is first give sigma ij definition. The other is first write down this and give. Maybe the other one is better. So anyway, so based on this, we give the definition of the stress tensor definition, which sigma ij, 2 index I and j. J correspond to the direction of the force. So whenever you see a stress tensor component, you want to see which direction is it pointing to. If it's pointing to the y direction, then the second should be 2. The j component should be 2. If it's pointing x direction, then the j component should be 1. As it is. And previously, I already wiped it. We defined stress as force by the area. So denominator is area in the j's direction. I's direction, which means the surface that this stress tensor component is lying on. For example, this stress tensor component is lying on the y surface or the 2 surface. That's why it's 2, 2. And this stress tensor component is lying in the z direction. There's sigma 3 because it's on the z surface and pointing towards z direction, 3, 3. And so on. And for any random continuum body, if you take a small piece of the surface, you define the surface normal direction as n. It's a normal direction of this surface. And there's a stress tensor on this component. Then the stress component on this given this normal direction is sigma ij and j. J is a dummy index, so what should be the free index? Free index should be I, and then we can use previously I defined an attraction. That is in the i's direction. So as I mentioned, J is a force in J's direction, and I is a surface direction. Okay, so we already defined what's a strain tensor, what's a stress tensor. That's pretty much the most of the content of the class. And eventually, we previously learned how do we transform the coordinate system to represent the same strain tensor. We can similarly apply that to stress tensor. So if I have sigma under the coordinate system PQ, and want to get the sigma under coordinate system ij, what's the value? Then we want to represent tensor into values, written in the form of matrix. How do we apply the transformation, the rotation process? Similar to that, we have 2 indices, P and Q. We want to transform them to ij, so we want to apply the transformation or rotation to P and Q respectively. So we have 2Q rotation matrix. One takes care of Q to J. The other takes care of P to I. Cool. And great. So now we learn what is a stress tensor. We also learn what is a strain tensor. Let's say now we don't want to write ij. Say they're in different coordinate. So we have epsilon KL, second order tensor. Stress sigma ij, also second order tensor. So what is the relationship between sigma ij and epsilon KL? If you recall from the first three examples, we use the thing called Hooke's law, which you guys are already very familiar with. So you learned many years ago, I was in high school. Then intuitively, you would guess they're related by the Hooke's law, and you're most likely correct. But here we call it generalized Hooke's law. Why is that? Because it involves different coordinate system. So let's assume it's represented in the real space. The real space, sigma ij, if we write other coordinate system into a matrix, then it's a 3x3 matrix. And epsilon KL is also a 3x3 matrix. So how do we map one 3x3 matrix to the other 3x3 matrix? How do we map it? The answer is simple. According to Hooke's law, the stress is linearly correlated with strain by a constant. It can be called elastic constant because we're in the elastic regime. So basically here we have stress sigma ij, strain epsilon KL. We need a fourth order. This is a second order tensor. This is a second order tensor or rank 2 tensor. We need a rank 4 tensor to represent the transformation between the from index KL to IJ. It's IJ KL. And what will be the dimension of the fourth order tensor, or how many degrees of freedom do we have? Since this is 3x3 in the form of matrix, this is 3x3. This will be 3 by 3 by 3 by 3. And in this lecture, for now, we learned that this has 9 components. It has 9 components. It has 81 components. We do the algebra 3 times 3 times 3 times 3 to the power 4, which is 81. But for this class, you will learn that we don't need to do the calculator that complicated. So it can be reduced to much lower degree of freedom using symmetry. There are one major symmetry, which will not be covered in detail today, but you will learn later in this class, which is Cij KL equals CKL Ij. And 2 minor symmetries. One is, anyway, I'm just going to put it together. So Cij KL equals Cij LK equals Cij KL. Sorry, JIKL. After applying the major symmetry of the elastic constant, which later you will understand to justify why it's like that physically. But now if you take it as it is, you just trust us, then it can be represented to 21 components from 81 to 21. And it can be also eventually further reduced to 2 individual components, the bulk and shear moduli under isotropic assumption. Final comment. This is a fourth order tensor. So how do we transform the coordinate system to represent the fourth order tensor in different coordinate system? So let's say I want to get a new IJKL. Sorry, I'll get IJKL from coordinate system MNPQ, or ABCD, whatever letter you want to name it, right? Just apply the rotation matrix that takes care of indices Q, P, and M to L, K, J, I. So from Q to L, from P to K, from N to J, from M to I. This is how you transfer the coordinate system to represent the same fourth order tensor. And so for now,